Here we're now up to 8.3, which is about geometric sequences and series. There'll be a few examples here, but mostly I'm going to show you how to get the formulas for series and sequence and just kind of give you the overview so that you've got those as tools available to you. Most everything in the section is going to be pretty similar to what you've been doing, just with the addition of those formulas. So the first thing we'll start you off with here is a recursive function that we want to write as a geometric function. Now, I haven't given you the formula yet, so this is a good kind of exploration type problem. But remember, recursive, to generate a recursive sequence, you have to go in order. You have to get the first term, you get the second, you get the third, and so on. If you just have a geometric formula, you can find the 1000th term instantly if you want to, instead of generating 999 in front of it. So that's the advantage to having a geometric formula versus recursive. So let's start by writing some terms out. A1 is going to be 2. The second term, you'll plug 2 in here, so 3 times that is 6. Third term, you'll plug in 6, so 3 times 6 is 18. Fourth term, you'll plug in 18. 3 times 18 is 54. And hopefully that's enough to kind of get you started to see a pattern. So let's say A1 is 2. And let's use 2 to get the other one. So to get the second term, we take 2 and multiply by 3. To get the third term, we start with 2 and multiply by 3 twice. To get the fourth term, we started with the 2, we multiplied it by 3, got to there, multiplied by 3 again, got to here, multiplied by 3 again. So hopefully a pattern started to emerge here. And that might be a helpful way to get the formula. Now I'm not defining the formula quite yet. If you see where it's going, that's awesome. We're going to define it in the next example. But right now I just want to I want to come up with a formula, just I'm not defining the geometric formula quite yet. So AN definitely starts with 2, and then it multiplies by 3 pretty consistently. And this is probably kind of naturally where you would start thinking. That's where most people start kind of thinking about, is they're seeing exponents happening. The only difference is, check out how this exponent compares to the term you're on. If you're on the first term, this is to the 0 power, because it's just 2. This isn't there. When you plug in 2 here, well, you're only doing 3 to the first. 2 times 3 to the first. When you get to the third term, it's 2 times 3 squared. So that power is 1 less than whatever your term is. And that should do it. If we plug in 1 here, that's 3 to the 0, that checks out. Plug in 2 here, that's 3 to the first. 2 times 3 to the first is 6. So that seems to be working, and that's the beginnings of your formula. Okay, so now formalizing this, we want to find the 8th term in the sequence. Now this is one I intentionally picked that you could do this pretty quick without a formula. And I'm going to go ahead and do that. But if I had asked for the 100th term or something like that, we really don't want to have to list out all those terms. We want to get a formula that gets us really quick. So we're multiplying by 2 each time. You can probably see that pattern. So 16, 32, 64, 128. And that would be the 8th term. There's 4 more. That's the 8th term. So I can get that pretty easily in this one. Let's take that same approach that we looked at on the last example. The first term is 1. Let's think about what we can do with 1 to get the next term of 2. Well, that would be 1 times 2. Third term is 4. So what would I do with 1 to get 4? I multiply by 2 twice. And to get the next term, 1 times 2 times 2 times 2. So it's starting to follow that same pattern we just saw. And that's really what I want to reiterate, is we're starting to see the same pattern show up twice. So our first term, let's look at the key things. First term is 1. This thing you're multiplying by each time, that's called a common ratio. It's called R. So R equals 2. You multiply by 2 each time. We'll do something like that. And again, that's called a common ratio. So common ratio is 2 in this case, and we use the letter R to represent common ratio. All right, so let's use some of these key ideas we have to formalize or get a formal formula here. So I'm taking 1 each time, and I'm multiplying it by 2 to the n minus 1, because first term there is no times 2. In the second term it's 2 to the first, 2 squared, 2 cubed. It's always 1 less 2, or 2 to a power less than the term you're on. So n minus 1 there. Following the same pattern as before. And let's look at where these pieces show up. So A1 is that 1 right there. This number 2, that is our R, common ratio. And then n minus 1 is just going to stay there the same. So let's make this formal, finalize it. We've got A1, first term, times R to the n minus 1. And that's your formal definition for a geometric sequence. The geometric series formula is not quite as straightforward as the other formulas we've covered in this chapter. It's another one of those cases where someone had to just sit down and kind of mess around until they found a strategy that made a lot of sense. But I'm going to walk you through it. I think it's kind of a fun thing to derive here. So let's start with kind of how it would go if you were just going to come up with the sum of a geometric series, or geometric sequence to get the series. So you would begin with the first term. And then the second term would be A1 times R. And then the next term would be A1 times R squared. And then R would continue increasing. And this pattern is going to continue until you get to A1 times R to the n minus 1, because that is your A sub n, your last term. Whatever value n is, when you get to A sub n, by the sequence definition, that's it right there. Now here's where the fun little trick comes in. What if, and again, it's just a what if, somebody played around until they had tried something and it checked out and it made it easy. So logically, or by the rules of algebra, it's okay if I multiply this by R. So the second time here, I'm just going to multiply by R, okay? Which means I'm going to multiply all those by R. So instead of A1, this is A1 times R. Instead of A1R, this is R squared now. This is now R cubed. Sometimes the ending can be kind of tricky on this, and there's a lot of ways to look at it, but since the exponents are counting up, the easiest way to think about it is just what's 1 more than n minus 1. So if you added 1 to that, it would just be R to the n power. So if you multiply the whole series by R, it now looks like this. And here's the other little trick we're going to try. What if we subtract these from each other? So we've got two equations, and I'm going to subtract the 2 from each other. So on this side, I'm going to have S sub n minus R S sub n. Over here, everything that's the same is going to subtract out to nothing. So A1 times R, A1 times R squared, R cubed is going to be in there somewhere. And everything got shifted up 1. So if it helps, right before this term was A1 times R to the n minus 1. And then the next term was R to the n. So that part is going to cancel out or subtract out as well. So the only thing left now is the first term minus, because you're subtracting all this stuff, A1 times R to the n. And if I'm going to solve this thing for S sub n, we're going to need to do a little bit of factoring. So let's take that step. S sub n equals 1 minus R. And I'm going to go ahead and factor here. You can, you don't have to, but I think it's easier if we do. And the formula, you're generally going to see it factored anyway. So let's take that step. So again, I took A sub 1 out of both terms. I'm trying to get S sub n by itself, so the only thing left to do really is to divide by 1 minus R. So that's going to be, and that's going to do it. So S sub n equals A sub 1 times 1 minus R to the n over 1 minus R. So it's a little lengthier formula. It's a little bit more to memorize. I think it's kind of worth it to see how you derive it. So it's not, it just looks kind of made up, honestly, if you don't derive it. So hopefully that kind of helps you see that part. Finally, we're up to infinite series. These are series that you literally can add terms forever. Now we talked about with arithmetic, that always goes to infinity or negative infinity. It's kind of useless to do it. There will be cases where you get a total with geometric series. So we're going to talk about that. With arithmetic, when it goes off to infinity, that's called divergence. That's a calculus term. When a series actually closes in on a value, and I think once you see an example, you'll start to understand the term. Because it never quite reaches that total, that sum, but it gets really close and you can tell where it's going. And that's called convergence. The series is converging to a definite point. So if it goes off to infinity, it's called divergent. If it's closing in on a particular point, it's called convergent. And that'll, again, be a big topic in calculus. So we're going to start the formula, and I'm going to take a step back because there's going to be some scenarios we got to look at. So let's just begin with our geometric series formula. But instead of n, I'm going to use infinity because that's what's going on here. So there's our formula. And now let's kind of think about what could happen. R to the infinity right off kind of feels like that's just going to go off to infinity. There's really three scenarios you got to look at. Over the years, to show the three things that can happen, I've come up with these scenarios: the rocket, the pendulum, and the bouncy ball. And I'll show you why as I go through each one. So first up, let's think about a rocket. And if you already know all the astrophysics stuff, let's keep it simple. If a rocket is firing its engines, it's going faster and faster and faster. That's all. I'll stop at that, okay? So if it went 2 feet 1 second, and then 4 feet the next, and then 8 the next, and 16, kind of like that series we saw earlier, sequence we saw earlier, then if it could do that forever, I know it can't, but if it could do that forever, how fast would it be going? Well, forever, the answer would be infinity, right? Now, pendulum, all right, just swings back and forth. Now, in theory, the friction, nothing like that, perfect, everything's conserved, the same amount back and forth each time. So, let's say it covered 1 foot every time it went back and forth. All right, 1 foot here, another foot here, another foot. So it'd be 1 plus 1 plus 1 plus 1, oops, forever. Okay, it's 1 plus 1 plus 1 plus 1 forever. That also has infinity. So if it never slowed down at all, it would cover an infinite distance. And that brings me to the bouncy ball. Now, if I drop a bouncy ball, it's really hard to do on camera, so I didn't do it for real. I thought that was a fun picture. A bouncy ball, it comes, like if I drop it from here, it's going to bounce up almost to there, and then almost to there, and then almost to there. It's going to do a little bit less each time. So let's say it does, let's say it bounces a foot one time, and then half a foot the next time, and a fourth of a foot the next time, and so on. Well, we can do some math, and that's where this is going. That would close in on a definite distance eventually, because at some point the ball is going to stop moving, and I can stop and add up all the distances. Now, if you want to get real technical, the molecules are probably still moving a little bit. It's sort of like an asymptote, and the way I always illustrate an asymptote is I walk halfway toward the wall, and then I walk halfway again, and halfway again. And there's no limit to how long I can go halfway, but at some point it's really hard to even perceive I'm moving. So kind of the same deal, but it does converge to something. So let's say it has a total for now. So the difference is here, the rocket is speeding up. The terms are getting further apart each time. Pendulum, the terms are the same distance apart each time, but they're not slowing down. The bouncy ball is slowing down. The distance between each term is getting smaller each time, and eventually it stops. That's really the key. Rocket doesn't stop moving. Pendulum doesn't stop moving. Eventually the bouncy ball does. So if you got a situation where it's showing that it's trending towards stopping its motion, and I'm saying that with motion lightly because we're going to look at just pure numbers, but if you see it trending toward a stopping point, it's going to converge. That's the calculus term. These two are going to diverge because they're not trending toward a stopping point. They're trending toward being in motion forever. So back to our formula. This is the formula. Now we need to refine it a little bit. The only case that this is going to happen is if, let's put a little if here. We'll formalize this in a minute. If R, let's think about what R is here. I guess we need to define that. So in this case, R is, well, it's bigger than, I don't want to give it away yet. Let's start with the pendulum, I guess. So this one should be pretty easy. What are you doing to go from 1 to 1 to 1 to 1 again? What do you multiply 1 by to get 1? You multiply by 1. So R equals 1. That's kind of our baseline right there. Let's compare to 1. So in this situation, R is bigger than 1. You think about that, if you multiply by 1.2 even, or multiply by 2 or 3, your terms are going to get further apart each time. Here, you're multiplying by something less than 1 because your terms are getting smaller each time. Think of that as you're dividing by something. But dividing by a whole number, or anything bigger than 1, is like multiplying by something less than 1. So that's the key. Your R value, the thing you're multiplying by, if you just think about what you're multiplying by, multiply by half each time. When you multiply by something less than 1, that's when it converges. So the only time it's going to converge is if r is less than 1. Now we'll formalize that in a second, but let's play with that scenario and see what happens. So if r is less than 1, let's say it's a half, and you raise a half to the infinite power. Well, that's hard to do, but maybe raise it to the second power and the third and see what happens. Well, 1/2 squared is 1/4. 1/2 cubed is 1/8. 1/2 to the 4th is 1/16. Those terms are getting smaller and smaller and smaller. They're trending toward being 0. So if you put in an r value that's less than 1 here, then you're going to get a1 times 1 minus 0. That's where everything's trending. And whatever the r, let's just keep it r for now down here, because I really don't know. R can be anything less than 1. I can't conclude what it is, but I can definitely conclude this is trending towards 0. If r is less than 1, then raise it to bigger and bigger powers. So the end result's pretty simple. It's a lot better than the original formula. It's a1 over 1 minus r if, and only if, absolute value of r is less than 1. Now, I kind of threw the absolute value at you real quick there at the end. Here's the reason. What if I've got 1 and I'm multiplying by -1/2 each time? Well, that's going to be -1/2, and then +1/4, and then -1/8. If you add those terms up, they're eventually going to reach a total as well. Eventually the motion is coming to a stop. That's what we call an alternating sequence, going back and forth, but eventually it's going to come to a stop. So if the absolute value of r is less than 1, you're going to come to a total, you're going to converge. I guess we could say if r is between 1 and -1, but that's just a much simpler way to write it. So let me box that in because that's your official formula there. But only if r is less than 1. Otherwise, it's just going to go off to infinity just like your arithmetic series always did.